So let's review how to find the area between two curves, and there's one formula and with two versions. So what we can do, we can solve two problems from each type with varied difficulty. So let's say we have two curves. Uh, so we have two curves. One is this. So that's the first curve, and then we have another curve uh, like that. So what we're trying to do, we try to find the area between the two curves between the value of A and B. So we can find the area between these two lines. So this is the first vertical line, that's the second vertical line. So the goal is to find the area between the two curves. So I hope you remember what we did. So what we're gonna do is we're gonna pick a typical point. So we're gonna pick a typical point. So we can call it xi star, and then we're gonna look at the typical area. So what we normally do is we draw a rectangle with the height at the value you pick. So that's the point you're gonna pick. So I'm gonna pick the point xi star, what we normally call the sample point, and then we're gonna find the area uh, with the height as the function value at the point. So we're going to pick the function value at the point. So in this case is so this is the height you get. So you can see the height is the difference in the y values of those two curves. So I'm going to call the first curve y equal fx. First means the top curve, and the bottom curve I'm going to call y equal gx. So if you say that, then what we can do is we can find the area of one such rectangle, what we call typical rectangle, at the point xi star. We're gonna call what we normally call the element area element. So we use a delta notation. So delta A, that's the area element. It is by geometry. It is the height times the width. So what's the height in this case? You can see the height is the difference in the y coordinate. So you can see height is the difference in the y coordinate. So that means in this case f x I star, that's the value at the top curve, minus the value as the bottom curve, because that's going to give you the height of the rectangle. So you subtract the two, top curve minus the bottom curve, and then that's the height, and then times the width. Width is delta x, so we're going to say delta x as the width. Um, so yeah, so delta x is the width. Okay. Now what we can say, that's a typical area element, what we call. So what we can do to find the actual area, what we can do, we can integrate this one. So if you integrate, so you're gonna get a is a to b fx minus gx is the top minus the bottom, always to get a positive answer. So if you subtract that, you get negative answer, you can consider absolute value. That's another way to do that. Yeah. Also, another way to remember that is what we're gonna do. Those are the y values. So y the top value minus y the bottom values. Okay, y the top values, y the bottom values, and the dx. So that is the formula. Okay, so we can use the formula. Let's do like two problems maybe, just to understand, just to remember what we did. Okay, so one thing you need to remember is, since this is the integral is in terms of x, this has to be a function of x. So it's very important. Those two has to be a function of x. Okay, function of x. The reason is you are integrating with respect to the x variable. Okay, so it has to be a function of x, and then it is yt, the top minus the bottom. Okay, so the top minus the bottom curve, that's the top curve minus the bottom curve. Good. Okay, let's try to do maybe two problems just to remember. So the first one is, let's say find the area of the region, find the area of the region, find the area of the region bounded by the curves, bounded by the curves, y equal ex and y equal x squared plus 1, and the line x equal 1. Okay, so that's the kind of situation. So always, like, a good idea would be to look at the graphs, because that's going to kind of tell you everything about it. So what's going to happen in this case? So you can see, let's graph them. So you need to know, like, a basic graphs. So y equal x squared, that's a parabola. So it's gonna go like this, pass through 1. Yeah, actually I'm gonna kind of redraw that. So it's gonna pass through 1, and then y equal x squared, that's also, that pass through 1. So that's kind of interesting situation. So what you're gonna get is, you're gonna go like that. So it's also 1. So your area is that. So what we're gonna do is, so this is y equal ex curve. This is the y equal x squared plus 1 curve. It passes through 1. Then what we can do, we draw the typical area element. So that's that. So we're gonna find the area of that small part. Okay, that's the at the x position. We normally use x when you do the calculation. Good. So what's going to happen is, it's very easy to find the top curve and the bottom curve. So that means the area is simply given by what are the limits? You can see this is the dx problem. Why is a dx problem? We're going to go in the x direction. You can see you're going to move the x. So it's a dx problem. That means you need the limit of x. So it is a to b, y top minus y bottom, and the dx problem. So let's put the numbers now. So a starting value is 0, ending value is 1. The top curve is x squared plus 1. The bottom curve is e to the x, and then it's a dx problem. You can see everything looks great. It's everything in x, so it's very easy to integrate. So it is x3 over 3 plus x minus ex, and then you need to evaluate this at 1 and 0. So if you plug in 1, you get 1/3 plus 1 minus e to the 1, which is e, minus, when you plug in 0, the first two are 0, so you get 0 minus 1. And if you simplify this, you will end up getting, so what's the final answer? So you can see you will end up getting 7/3 minus e. This is the area problem, so it is a unit squared. So that's what you get for the first one. So as a second problem, let's do this one. So we can do find the area bounded by the curves. Find the area bounded by the curves. Bounded by the curves. Bounded by the curves. Y equal x squared minus 1 and y equal x plus 1. Okay, y equal x squared minus 1 and y equal x plus 1. Again, as before, let's try to graph the two curves. Y squared x minus 1. How to graph that? You can see that when you look at y squared x minus 1, that gets 0 when you plug in x equal plus or minus 1. So that is one of the big fact that's going to help you to graph the curve. So it's going to be 0 at plus or minus 1. So 0 at plus or minus 1. Okay, so this is minus 1 and plus 1. And the other one, actually I'm going to put the number on the other side for a reason that will be clear later. And then the other one is y equal x plus 1, and you can see that that's also 0 at negative 1. That means it's going to pass through the same point. So the second one is going like that. Okay, so the goal is to so this is y equal x plus 1, this is y equal x squared plus 1. Good. Now the goal is to find this point because we need the integration limits, so we need to find that point. What is the point? So what we do that for intersection points, so for intersection points what we can do, we can set them equal. We're going to set the y values equal, so that means means x squared minus 1. You're going to set the other y value, that means x plus 1. You're going to set them equal and then bring it to one side, so it's x squared minus x minus 2, which has nice factors, x minus 2 and x plus 1. That means x equal negative 1 and 2. Okay, negative 1 we already have, so the value is 2. So that means that's the integration limits. Okay, now what we can do, we're gonna pick a typical x and draw the area element. So we're gonna pick a x and draw the area element. So that's the area element. Uh, Good. So that's the one we're gonna find. We're gonna find the area of one of them and then integrate. So this is like an easy problem now. So what we're gonna do is, so we can write the area. So area is simply again a to b, y the top curve minus y the top curve minus y the bottom curve, and dx problem, because you're going to see you're going to integrate along the x direction. Okay, you can see the strip moves from left to right. Okay, from left to right. So the typical piece moves from left to right. Good. That's why it's a dx problem. Now we're gonna plug in the numbers here, plug in the values. So a equal negative 1, the starting value, ending value is 2. The top curve is x plus 1 minus the bottom curve is x squared plus 1. Actually, it's not x squared plus 1, is x squared minus 1, because it can be x squared plus 1 minus 1. And here also x squared minus 1. Okay, so and then you can see we can simplify inside, so it is negative 1 to 1. If you simplify inside, what do you get? You can see that you're gonna get 2 plus x minus x squared dx. It's very easy to integrate, so if you integrate you get 2x plus x squared over 2 minus x cubed over 3. Yeah, so and then what we're gonna do, we're gonna evaluate this at the 2 points. So it is 2 and negative 1. So we're gonna plug in 2 first. If you plug in 2, you're gonna get 4 plus 2 minus a third, minus, if you plug in negative 1, you get negative 2 plus 1 half, and then plus 1/3, because the negative 1 cube is negative 1 with the negative sign is positive. Now how to simplify this? So you can see it's very easy to simplify. Combine these two, that's like one of the trick we can do. Combine these two. When you combine these two, because since both are negative, the top gonna add, so it's a negative 9 over 3, that means negative 3. So after you simplify, you end up getting 4.5. This area problem, so it is unit squared. So that is the answer. That's the area you were are looking for. Okay, so that's the area of this region. Good. Now I'm gonna give you some practice problems. Uh, let's go with this method. So let's try this. This is exercise. So I'm gonna call this is 5A. Um, so I'm gonna call it just one problem. I'm gonna call 5. Let's do it like that. Call it 5 and then ABC. Okay, find the area. Find the area bounded by the curves. Bounded by the curves or lines. Okay, line is a curve. So the first one is try y equal x squared and y equal 2x minus x squared. When you graph this, think about this a parabola, but concave up or concave down. It is concave down because it's a negative sign. You see the negative sign? It's a concave down parabola. Okay, you need that. And A, and then B. This one y equal x minus 1 and y squared equal 2x plus 6. Y squared equal 2x plus 6. Good. Okay, let's try those two problems. So what we're gonna do, we're gonna move to the next one. We are not gonna do a problem from that, but that's a special case. So let's look at this special case. Special case. What's gonna happen? Sometimes these curves cross each other at more than one point. So for example, you can have one curve going like that. The other one is going like this. So if this happens, you can just integrate this one because it's not going to give you the answer. So let's say you want to find the area, enclosed area between these two numbers. So what you're going to do in this case is you need to find what are these points as well, all the intersection points in the middle. So CD. Now what we're going to do, we're going to split. So I'm going to say the top curve is F, but you can see it's going to be the bottom curve and the top curve. And this is the bottom curve. Now it's going to be the top curve and the bottom curve. So that means you have to split the integral at those points, and because the area is simply the area of the absolute integral. Okay, so if you have the area problem, so area is now going to be a to b, the absolute value fx minus gx dx. This always works. But the problem is when you try to integrate this one, you can't just integrate like this. What you want to do, you have to split the integral at those intersection points. So you're going to do the first one a to c. The top curve is fx minus the bottom curve is gx. And then plus the next one is the top is from c to d. The top curve is gx minus the bottom curve is fx plus d to b. The top curve is fx minus the bottom curve is gx. So that's what I have. Okay, so you have to split the integral and then you can integrate. So I'm going to give you two problems. You can try these as a problem exercise. Only thing you need to find the limits now. So let's say so this is 5C. Again, find the area enclosed by the curves. Okay? Find. Let's try like that. So I'm gonna curve. Let's get the problem. So find the area enclosed by the first one is sin x. It's not a actually, it is c now. So c sin y equals sin x, y equal sin x, y equal cosine x, and x equals 0, and the line x equal pi over 2. That's the first one. The D, this is like a little really interesting one. Uh, y equal x cube minus 3x and y equal x between those two curves. And you can see once you graph this, you can see it's going to cut at 3 points. Because it's a cubic graph, this is y equal x line, it's going to cut at 3 points. Okay, so that's a special case. You can try them and you can find the answers in the description. So let's go to the last type. What's going to happen? There are moments that you cannot do this anymore. So let's try to talk about that. So the next type is, so it's area between curves again, area between curves. So what's going to happen is you're going to integrate with respect to y. Integrate with respect to the y variable. Okay, so good. So this is the situation. So let's say you have a graph. So graph go like that. So if the graph goes like that, the problem is you can see they are not functions of x anymore. So what you want to do is you cannot do the way we did it. So you have to graph. So let's say you want to find the area from C, this curve to that curve, that line. So the problem is they are not functions of x anymore. So that means you cannot do the way we did it before. So what we're going to do, we're going to strip the other way. We're going to do it like that. We're going to do it like that. So that means it's a dy. It's not dx anymore. It's a dy. So you pick a typical y, but it's a dy problem now. Okay, so you have to integrate the other way. So this is the area you're going to get. But you can see the previous technique does not work anymore for this problem. Okay, so the curves are now what we can do, we can write the curves, we can solve for the x coordinate, because what you want to do is this, the height of this strip is the difference in the x coordinate, not the y coordinate, the x coordinate. So you need to find the two x coordinate, the two one. Okay, so x to the right and x to the left, you need to find those two coordinates. The difference between those two coordinates are the height, is the height. Okay, so what we can do, we're going to solve this curve as a function of y. So we can write this as a function of y. Do the same thing, we also solve this one as a function of y. So we can say x equal the function of y, we say gy. Okay, you can see that's the major difference. There you need to solve for x, because you need the difference between the x coordinate. So you have to solve for x first. Good. So let's say you did that, and then what you can do, you can write the typical area element. So the typical area element is as before. So what we can do is you have the x coordinate now. So we subtract the x coordinate. So it is a but as you solve for the y variable, since they are, so you solve for y variable. So what you need is xr minus xl, but these times delta x, not delta x, is delta y now, delta y. So but x r you solve, so it is the function of y minus function of not the same function, gy, and then we times delta y. So you can see this is a function of y now, not function of x as before. So that's the major difference. So that means your area you can write as again c to d now, and then the function on the left side, see there are function of y, function on the right, not function on the right side, and then function on the left side, and the dy. So in short, we can write this one as c to d x r function on the right minus function on the left times d. You can see the strip go top up down, so it's a dy. Okay, so that is the formula now. Good. Okay, let's try to solve two problems from this type as well. So this is the problem. So let's say find the area. Find the area enclosed by the curves y squared equal 2x plus 5 and y equal x plus 1. So let's say those two are the curves. Okay, how to graph them? So what is the shape of y squared equal 2x plus 5? How do you think about it? You can see it is a y squared. That means y get two values for every x value. Is that right? Y get two values. For example, if x equals 0, y equal plus or minus square root 5. So that means it is the other way. Right? It's the other way. So so let's graph. So when you apply x equals 0 is plus or minus square root 5. So I'm going to graph it here. It's always helpful if you graph the curves before you do the integration. Okay, so for each value you have two y values. That means, and when you plug in, and it's also symmetric about the x-axis, okay, because of y squared. So we're gonna graph it. So it's gonna be like this. Gonna go like that and go like that. Okay, that's that part of the graph. Now the other one is the straight line. That's easy to graph. That means when you plug in x equals is passed through 1. So it is y equal, yeah, when you plug in when you plug x equals it is y equal 1. So that means that's the graph. Go like that. Okay, so that's it. Now your goal is to find the height. So it's the same thing. But the problem is, can you use the idea that we used before? Because if you try to do that in the first part, you can see you have to evaluate between two curves. Okay, so especially if you look at this side, this part right here. See, you can see it's the same curve top and bottom. So that means if you simplify it, it's going to be very complicated. So because of that, we are not going to do it that way. We're going to do the other way. Okay, so we're going to strip the other way. So that's what we do. So that's the difference of why we cannot do the other way. You can, but it's complicated. You get the same answer, but through a complicated integral. So we're going to do it this way. Okay, so what we're going to do, we're going to find the x coordinate of the right side, x coordinate of the left side, and then subtract the two, and then integrate with respect to y. Okay, so before we do that, we also need the limits. So what are the integration limits? So we need the limit of y. So it's the same thing as before, but need the limits in the y direction now. Okay, so for that we're gonna so the first thing we do is we're gonna solve for, because you have to solve for x. So let's solve for x first. So we have y squared equal to x plus 5. So we're gonna solve for x. So x is how much you get 1. So you subtract and take half. So 1/2 y squared minus 5. That's 1. The other curve is y equal x plus 1. This is easy. This is x equal y minus 1. Okay, that's first thing to do. You solve for the two. So which one is the right one? You can see this is the left one. This is the right one. Okay, that's important. What is the left curve and what is the right curve? Okay, good. And then also we need to find intersection points. So for intersection points, we can set them equal. Okay, in this kind what we can do is we can set y squared equal, not y but y squared. So let's do that. So we're going to set y squared equal, that means x plus 1 squared equal, that one already there. Okay, so this can give you what this can give you. So you can see that this x squared plus 2x plus 1, this is 2x plus 5, and you can see this get cancelled. So that means x squared equal 4. So that means x equal plus or minus 2. So you get x equal plus or minus 2. And then what we can do, we can plug in those values to one of those equations. The second one is easy. And then calculate the corresponding y values. So you can see if you plug in x equal 2, y equal 3. If you plug in x equal -2, y equal -1. So those are two numbers. That means your integral gonna go from -1 to 3 because you need the y values. Okay, so we have everything we need. We know what is the left curve, right curve, and we also know the limits is going from -1 to 1. So we can write the integral now. So let's write the integral. So the area is is a to b, the right minus left, a dy problem. That means everything has to be in terms of y. That's why we solve for y. Because you can integrate this otherwise. Okay, let's plug in here. So it is -1 to 3. XR, the right curve is y minus 1 minus the left curve is 1/2 y squared minus 5 dy. You can see everything in terms of y. Everything looks great. So now what we can do is it's going from -1 to 3. If you simplify, you get -1. It's a good idea to simplify. And then y, and then plus 3/2. So it's gonna cancel out some unnecessary simplifications. Okay, so now we can integrate. If you integrate, you get -y3/6 plus y squared over 2 plus 3/2 y. You're going to evaluate this between 3 and -1. So if you plug in 3, you're going to get -9/2 plus 9/2 minus, if you plug in -1, you get 1/6 1/2 minus 3/2, and then if you simplify all of them, you end up getting 16/3. It's area, so the unit squared. So that's the final answer you get for that. Okay, so as the last problem, I'm going to do like a little complicated problem with some special simplifications. So that's the fourth problem. We do example. So let's say find the area enclosed by the curves x equal y squared minus 3y, y equal ln x, and the lines are y equal 2 and x-axis. Okay, so that's the problem. Okay, so the first thing is you need to look at the shape of the graphs, and you can see we can factor the top one. So this is y minus 3. So that's a parabola. And then you can see that is x gonna be 0 when you plug in y equals 0 and y equal 3. So we can use that facts to graph it. So that means so how it look like. So it's gonna be 0 at y equals 0 and 3. So it's going to be 0 at y equal 3 and 0. So it's going to look like this. Okay. And then that's the first one. So it's going to be 0 and 3, y equals 0. And the other one is just the natural log graph. So we can graph it. That's the natural log that we know. The shape is like that. Okay. And then what's the other line? One line is y equal 2. So that line passes through here. Y equal 2 line. The other line is y equals 0. I mean, it's x-axis. So that's that. So that means that's the other line. So that means so we can try to find the area we try to find the area in this region. Okay, so find the area of this region. So this is the area we are interested in. Now you can see that if you try to write the integral in the first small part here, right here, in this small part right here, there's a problem. Because if you try to write the integral in the x integral, you can see you need to find the top and bottom curve, but the top and bottom curve are exactly the same curve right now. So I mean, if you try to solve for that, it's going to be complicated. You have to use a quadratic formula and a lot of stuff. It's just to get the same answer, but it's very complicated. So we are not going to do it like that. So because of this issue, we're going to do the other way. We can do a y integral. So we're going to strip the other way. So we're going to have the typical area element along this direction. Okay, so that's the goal. So we do it like that. So you can see, so the thickness is in the dy direction, y direction. Okay, that's a dy problem. So you have to slowly go with the y values. So we need to know limits of y in this case. So we know what value, one value starts 0, the other value go up to y equal 2. Okay, so what are the other curves? One curve we already know, we know the left curve already. So I'm going to write this as XL curve, which is y squared minus 3y. The other curve we need to find it. So we know that the y equal ln x. So by the definition of natural log, we know that the x equal e to the y. So this is not just x, this is the right curve. So we write x r. And then we already know what is the xl, which is y squared minus 3y. Now we have everything we need. We already know the limits, so we can write the integral. So area is simply a to b, the right curve minus left curve dy. You can see the thickness is in the y direction. Okay, now let's plug in. So the limits are, one limit is 0, the other limit is 2, and the right curve, what's the right curve? So you can see that's the ey minus the left curve is y squared minus 3y dy. You can see everything in the y, so everything looks great, so we can just integrate. We can simplify before we do it. That's always a good practice. So it's y squared plus 3y to avoid unnecessary calculations. Okay, now this is easy to integrate, so you can see you're gonna get ey minus y3 over 3 plus 3 halves y, and then you're gonna integrate between 2 and 0. So let's plug in the values here. So if you plug in the values, you're gonna get e squared minus 8 third plus 6. That's the first one. Minus, you can see when you plug in 0, you get 1. Everything else is 0. So if you simplify, you get e squared minus 7 third. And then you can see this is a area, so this is a unit squared. Okay, so that's it. I'm gonna give you some practice problems, so you can try these. So exercise. So you can say find the area enclosed by. Okay, find area. Find area. Find the area enclosed by. Same problem. Enclosed by. So we have E now. How about this one? Y equal 1 over x, y equal x, and y equal 1/4 x. This is an interesting problem. And F, you can try this one. This is similar to one we just did. X squared, y squared x plus 2, y equal ln x, and then the lines are between y equal 1 and y equal -1. And G, the last one, you can try x equal y squared minus 4y and x equal 2y minus y squared. You can see two parabolas, one curve up, one curve down. Okay, you can try these for practice.